Hi everyone, welcome back to our channel. Today we are going to discuss about what is meant by an self-inductance, what is meant by mutual inductance and the derivation for coefficient of coupling. Okay, so this is very important as per our curriculum is concerned. Okay, now we are going to see the derivations for all these things. Okay, so hope we will continue with the video. So all this comes under the concept called as analysis of coupled circuits. Analysis of coupled circuits. So here we will try to understand what is meant by an self-inductance, what is meant by an mutual inductance, and how the coefficient of coupling. So remember, we need to get the derivation for coefficient of coupling is equal to mutual inductance of the inductors divided by root of L1 and L2. We need to get this derivation. To get this derivation, so we need to learn some few concepts which are called self-inductance, mutual inductance and the coefficient of coupling, which is K. So now generally let's try to define. The first one is self-inductance. So what is self-inductance? So you may ask a doubt, difference between inductor and inductance. Okay, so this is nothing but the inductor. So this is an inductor. The property of the inductor is nothing but inductance. Now, what is self-inductance? Actually, how we generally describe is, we will generally apply some voltage to an inductive coil. Okay, so we will try to apply some voltage to an inductive coil. Voltage we apply, which is a function of time, automatically this will develop some current which is nothing but I of t. This I amperes of current flows into n number of turns in the coil divided by the magnetic resistance of this coil is going to generate a magnetic component which is called as flux. Now this flux will be generated and this flux will be moving the path what I have been shown. So if the flux is generated, automatically as per the Faraday's laws of electromagnetic induction, and EMF is induced by the formula 4.44 flux into frequency into number of turns. So flux is already generated, frequency of the supply is 50 Hz. Let us assume here we have 5 turns and n is equal to 5, and let's try to understand some the voltage of some 10 volts is induced. That is what we have from Faraday's laws of electromagnetic induction. So here when you see the formula for the voltage across an inductor is the voltage across an inductor. So we applied what? Voltage. So voltage is directly proportional to rate of change of current. So I'm saying voltage, if you apply, it is directly proportional to the rate of change of current, which is di by dt. So why it is changing means due to a property which is called as inductance. V equal to L di by dt, where L is called as constant of proportionality, so which is called self-inductance. So L is called as a constant of proportionality which is called self-inductance. We can call this as a constant of proportionality. So this is a constant of proportionality, we call it as self-inductance. So now we need to link and we need to get the formula for inductance. Okay, so already we know the formula for inductance. Okay, the formula for an inductance is flux linkage by ampere. It is defined as a ratio of flux divided by ampere. So flux linking means, so flux, what is meant by flux? Flux phi linking n number of turns divided by the current is defined as the property of an inductor. So this inductor, so So now I require the value of I now. So I is equal to n phi divided by L. So use this value in this expression. Okay. So when you use this, V is equal to L d by dt of n phi by L. So V is equal to, we can write down it as, so 1 by L is a constant, we can write down, and n is also an constant, we can write down it as d phi by dt. L will get cancelled out, therefore we can write down V is equal to n d phi by dt. So these formulas are very much important. The voltage across an inductor is number of turns multiplied with change of flux divided by time, change of time, which is nothing but V equal to N d phi by dt. And already we have the first equation here, and the formula for voltage across inductor is also 2. So now let's try to compare each equation. The first equation is, we are going to get V equal to L di by dt, that is equal to N d phi by dt. So now we can compare both the equations. So when you compare both the equations, I can write down, so dt get cancelled, we can write down L is equal to N change of flux divided by change of current. The inductance is defined as, so number of turns multiplied with change of flux divided by change of current. We can define the inductance. Okay, so this is how we define the inductance. So successfully we learned some few formulas. So this is a long term, this is called self-inductance. Now we studied only, so inductor is an element. The property of an inductor is nothing but inductance. Self-inductance is given by the formula V is equal to L di by dt, and the formula for inductance is flux linkage, flux linking n number of turns divided by current is the formula for inductance. The voltage across an inductor is given by the formula V equal to number of turns multiplied by change of flux divided by time. So the ultimate formula for inductance, L is equal to N d phi by di, is the formula for inductance. Now this is all about the self-inductance. So how we are going to say about mutual inductance? When you have two coils, so this is called as mutual inductance. What is mutual inductance? It's very simple. So I have a coil 1, I have another coil. So just to differentiate, I am drawing separately. So here a voltage is applied, it carries a current of I1. So here also an EMF may be induced. So the flux generated only in this coil is nothing but phi 11. The flux generated only in this coil, we call it as phi 22. The flux linking second coil to first coil, the flux which is traveling from second coil to first coil is called as phi 12. Okay, so this is nothing but phi 12 or phi 12. So what is phi 21? So what is this means? The flux of coil 2 linking coil 1. So actually the own flux is nothing but phi 11. Own flux of the secondary is phi 22, but the flux of secondary, I mean the flux of coil 2 is linking coil 1, that's called phi 2 1, and there is also the same flux which is also called as phi 1 2, so which links second coil. This is the flux of basically coil 1 which link coil 2. I can call this phi 1 1 or phi 2 as a flux, where this flux is called mutual flux. Okay, so this how we can understand the basic concept. If you want to more clarity, you can see here. For your more clarity, just redrawing the color. So this red color is nothing but the flux of the one coil. This black color is the flux of the same phi 2 2. Okay, phi 2 2. But there is a flux which travels from second coil to first coil. There is nothing but called as phi 2 1. There is a flux which travels from first coil to second coil, that is called as phi 1 2. So that is called the mutual fluxes. So now I want the formula for the voltage induced at the coil 2. So this is like a transformer action. Will give the supply at, so this may be an AC supply or DC supply, we don't need to bother much. So actually if it's a transformer, you should not give DC supply, you have to give AC supply. So an EMF is induced at the secondary. So now the formula for an voltage across an inductor, voltage induced across the secondary is equal to, so we already have the formula, V equal to N d phi by dt. So here this general formula. Now we have to write down for second coil. How many number of turns are there? N2 number of turns are there. In this N2 number of turns, the flux which travels from 1 to 2 is called mutual flux. This is called as d phi 1 2 divided by dt. So the EMF induced in the secondary depends upon the number of turns in the secondary and the flux which travels from coil 1 to 2, 1 to 2, where we call it as phi 1 2 divided by dt. And already this phi 1 2 is flowing only due to a current, where this current is nothing but I1. So due to the primary current I1, a mutual flux is generated. That flux we are going to call it as phi 1 2. So I can write down the one more formula of V voltage across the second inductor is equal to, this N2 is nothing but the number of turns in the secondary. So I can write down as one more formula, the mutual flux into d by dt, and this flux I'm going to write down as a current, which is nothing but di by dt. So these are the two possible formulas I can link each other. So the voltage across the second coil VL2 is nothing but the number of turns in the secondary, which is d by dt of the flux which is moving from first coil to second coil. This is the one formula, but the voltage, this is only due to this one coil, but there is a voltage due to the another coil, where this flux I am going to call it as mutual flux d by dt, and this mutual flux is available only due to the current from the primary side or primary coil. These are the two formulas we can link. Now let us try to compare. This is due to mutual flux of the secondary coil. This is also due to the mutual flux of the another coil or mutual inductance. So first mutual inductance we are going to call it as N2 into d phi first coil on the second coil divided by d2, and this is also called as mutual flux into the mutual flux is coming only due to the primary current, which is nothing but I1. So when you compare here, I want the formula for m. So dt will get cancelled. I can write down m is equal to n2 into d phi 1 2 divided by d I1. This is the original formula for mutual inductance. So where m is called as the mutual inductance from coil 1 to coil 2 is nothing but the number of turns, where phi 1 2 is nothing but the flux transferring from coil 1 to second coil. So that's why this is called mutual inductance. And this flux is transferring, the source is nothing but why flux is transferring first coil to second coil, how phi1 is coming due to the source I1. So this is the formula respect to second coil. So similarly we can write down the formula for mutual inductance with respect to primary. Okay, so this is with respect to secondary coil. So I'm saying here, so this we have been written with respect to secondary coil. Okay, now we are writing the formula for mutual inductance with respect to primary. That is nothing but rather than N2 will get N1 multiplied with d phi 21 divided by d I2. So phi 21 is the flux of coil 2, the flux of coil 2 linking coil 1 is called d phi 2. So why the flux phi 2 is coming? So this flux phi 2 is only due to I2. So already told very clearly in the starting itself, we will just apply the voltage. Voltage will develop current. From current you are going to get the flux. From flux we are going to get the EMF. This is what the relation between all the parameters. Flux is available. Phi 1 2 is there only due to the flux phi 1. This phi 1 is there only due to. So the flux second coil and the flux coil is due to phi 2 and phi 2 is only due to phi 2. That's how the relation between current flux. So this is all about self-inductance and mutual inductance. We will continue in the next class the derivation of an mutual inductance. Meet you in the next class.